Hello Year 12s and welcome back to Mathematics. In this video we're starting a new topic of a continuous probability distributions. So what this topic actually brings together is some of the stuff that we looked at earlier in year 11 where we looked at probability distributions and discrete probability distributions, and we're going to apply that further to look at continuous variables in particular. So that's what we're going to need to do. And for this topic, we actually combine some of the stuff that we looked at in the last topic, particularly with cumulative frequency, histograms, and frequencies. And also, we're combining that along with the stuff that we looked at in integration earlier in this year. So I believe last term, actually. So that's what we're going to be doing in this topic. Now, to start off, we're going to actually do a bit of recap over discrete probability distributions, which we looked at in year 11, and also cumulative frequencies that we looked at in the last topic. So that's what we're going to do in this first video, and also start talking about what a continuous probability distribution function is. So let's have a look here. Section 1, this is on page, let me just get the right page out. So hopefully you saw the post on Google Classroom about physical copies of this booklet. If you don't have a physical copy, that's okay. You should have a digital copy available on the Google Classroom for you to access as well and follow along. This is on page 4. Now this is one, so here we're going to do a little bit of revision over discrete probability distributions. Now this we had a look at in year 11, and just a reminder here, a random variable, so let's talk about this definition. A random variable is a numerical quantity whose value depends on the outcome of a chance experiment. And so we talked about this. This is that stuff where we did P of X is equal to a particular number. P of X is equal to X, small x. Okay, so when one particular aspect or attribute is of a given population, S can be measured by a number, we call that attribute a random variable. So here, if we can measure a random event, random changing thing with numbers, we call that thing a random variable. Officially, a random variable X is a function from the population S to numbers. So here we talked about this earlier, and so what we did with discrete probability distributions, we, for example, listed out all of the possible outcomes of an event, so 1, 2, 3, 4, and we had to make sure that all of these outcomes were numbers. We wrote down the probability, so 0.1, 0.2, 0.3, 0.4, and we could actually calculate things like the expected value or mean, and also the variance and of our variables, and also the standard deviation. So this one I believe was sigma. And so this stuff was actually very simple. What we noticed in the last topic was we can actually calculate this these discrete probability distribution stuff using a calculator when we were looking at the mean, variance, and also standard deviation of a set of data as well. Okay, now the first part is we just need to be able to describe whether or not these following variables are numerical or categorical. We actually looked at this in the last topic, so I'm going to skip over this example and move on because we've done it fairly recently. Now, here on this page, this is on page 5, we need to talk about group data and relative frequencies. Now, here in the first law or result, the relative frequency of an event occurring is an estimate of the probabilities. Probabilities, let me spell that right. So when we talk about relative frequency, we're estimating, it's an estimate of the probabilities of that particular thing happening. So here is an example where we actually need to apply this. Now this one, this is from the VCE paper. Let's just read what the question says. Jane drives to work each morning and passes through 3 intersections with traffic lights. The number X of traffic lights that are red when Jane is driving to work is a random variable with a probability distribution given below. So when the random variable that we're talking about is X. So X is a number of traffic lights that are red when Jane is driving to work. And so here, the small x just represents each one of the different things. So this is 0 red traffic lights, 1 red traffic light, 2 red traffic lights, 3 red traffic lights. And underneath, this P big X of equal to X is just the probability of each one of these things occurring. So here, this one here, 0.1, that means that the probability of that random variable being 0 traffic lights is 0.1. That's what this means. Okay. Now the first part is, what is the mode of X? What is the most likely what's the most likely event for Jane? Well, for here, if you remember from our last topic on this descriptive statistics, the mode is the one that happens the most. So we're looking for the one that has the highest probability. Here, if we look at our table, the one with the highest probability is actually 0.4. And so here, the mode is just 3. The most likely number of of traffic lights that Jane is going to pass through is actually 3. The most likely is 3. Okay. Part B. Jane drives to work on 2 consecutive days. What is the probability that the number of traffic lights that are red is the same on both days? Okay, so let's just break down what this actually means. Jane is driving to work and she's doing it on 2 separate days, and we want to see what the probability is that each day she gets the same number of traffic lights. So for example, what's a good outcome would be if Jane got, so I'm just going to draw a tree diagram just to show me what this looks like. If Jane is driving to work on her first day, if she gets 0 traffic lights, then on the second day, the outcome that we want is that she also gets 0 traffic lights. So what's the probability of that? Well, for her to get 0 traffic lights, that would mean that it was a probability of 0.1. And then for the following day, if we want 0 traffic lights, that's a probability of 0.1. So the total probability of that particular line is just 0.1 times 0.1, or 0.1 squared, which just gives me, if I check that in my calculator, 0.1 times 0.1 equals 0.01. So here's 0.01. Now that's one possible outcome for Jane. That's if she got 0 traffic lights on both days. But how else could we satisfy this condition? Well, we just want the same number of traffic lights on both days. So here, if she got 1 traffic light on the first day, then the favorable outcome for the second day is she also gets 1. So that's 0.2 and 0.2. So 0.2 times 0.2, which I believe will give you 0.04. Hopefully you're starting to get to notice a pattern here. If we want this particular outcome, we just need to figure out, do the same thing, and we just have the same number of red lights each day. And so here that would be 0.3, 0.3, 0.4, 0.4, and we just times them, 0.3 times 0.3, 0.4 times 0.4, which will give you 0.09 and 0.16. Okay, and so once we've gotten all these probabilities, we just need to add them all together. And here I believe that the answer is, let me just check that, 0.3 as a final answer. So that's how we answered this question. I think we did a similar question when we did random variables earlier in year 11. So if you have your notes from that, that might be helpful to have a look at it, just in case you're not quite sure. Okay, we're continuing this section of just a quick review. Now this next part is relative frequency, histogram, and polygon. Now this is fairly similar to the frequency, histogram, and polygon. So if you remember from our frequency, histogram, and polygon, what we had was, when we drew our frequency, histogram, and polygon, we wanted to make sure that there was no gaps between our columns. And the other thing was, when we drew our polygon, we started from the bottom left and we went to the middle of each one of these columns, like so. Now with a frequency, histogram, and polygon, on our y-axis our frequency. So the frequency tells me how often each one of these scores happen. But with a relative frequency, histogram, and polygon, what we are showing on the y-axis is not the frequency, but if you notice here, that is our probability. What's the likelihood of each one of these events happening? Now, if you have a look, we're going to refer back to this example 2. We're going to refer back to this table in example 2. So I'm going to actually just write out this table here so that we have it in a reference to it. So here, this is a table that we're referring to. So here, our outcomes were 0, 1, 2, 3, and the probability Px of x is equal to 0.1, 0.2, 0.3, and 0.4. Okay, now, what we want to do here is we want to make this into a relative frequency, histogram, and polygon. So what we have in the notes here, there's no gaps in between each bar. So this is exactly the same as a frequency histogram. The polygon data point at the, let me just get my notes right, at the center. And so we actually talked about this as well. It's at the center of each of the rectangles. And commence at the end of one score value above or below the respective outside commence and end at one score value above and below the respective outsides of any rectangle. So here, what we want to do is we're starting from, if you have a look, the first x value is 0. So if you have a look at my Cartesian plane, 0 would be over here. And what we want to do is we just want to make sure that we've got a column, like so, either side. The next one would be 1, 2, 3. And we just want to make sure that our columns are equally spaced and also have the same width. And so that's why the column is going to go either like one score value above or below the respective outsides of any rectangle. So here, I'm now going to draw my columns, and with my probabilities, I'm just going to make it here. My probabilities go from 0.1, 0.2, 0.3, 0.4. And so just like we would normally do with a frequency histogram, we're going to now do it as a relative frequency histogram. And so the only thing that we've changed is we've shifted everything across a bit, and now we're doing the probabilities instead of just the frequency. So here, the first one, we had a probability of 0.1, like so. Next one was a frequency, relative probability, a relative frequency of 0.2. Next one was a relative frequency of 0.3. And then the last one was a relative frequency of 0.4. So here, that's what our frequency histogram would look like. Okay, and then our polygon, we're going to start one whole score over to the left, and we're going to just connect it with all the centers of our rectangles, and then we're just going to go to the endpoints there. So here, it's going to look like something like this. And so that is what our relative frequency histogram and polygon is going to look like. Now, the area of the rectangles in a relative frequency add to 1 when the width of the rectangles is 1. Now, the reason that is the case is because when you add the probabilities of all of these events together, well, all probabilities, when we add all probabilities together, it will always give me 1, because all probabilities make up the total sample space. So here, let's just check that. If we add up all the area of the rectangles, so each one of them has a width 1. So the area of each rectangle is just going to be 1 times the probability. So the area total would be 0.1 plus 0.2 plus 0.3 plus 0.4, which indeed gives me a total of 1. Okay, so that's how we do a relative frequency histogram and polygon. It's exactly the same as a frequency histogram and polygon. All we've done is just we shifted a little bit to the left, and instead we're using the relative frequencies or the probabilities of these events. Okay, now next one. Cumulative relative frequency histogram or polygon. Just like a cumulative frequency histogram and polygon, like if you remember from cumulative frequency histograms, what we did was we added up the frequencies all up until that point. What we're going to do now is we're just going to add up all the relative frequencies or the probabilities up until that point. So here, refer to the table in example 2. So they've given us this table, and we're going to plot the cumulative relative frequency. Now here, cumulative relative frequency, we're now representing that with x is less than small x. And so here, this is just telling me these are the probabilities of all of the x values which are less than or equal to that point, which is what the cumulative frequency actually tells me. So the way we filled this in, if you remember, we just added all the frequencies up until that point. In this case, it's adding up all the relative frequencies. So here, relative frequency, I've got 0.1. Next one, I'm just going to add on that 0.1 to the 0.2. So I've got 0.3. The next one, 0.6. And the final one, as we expect, it should be 1 because that is the total amount or the total probability of all events. The total sample space will always have a probability of 1. Okay, just like we did before, no gaps between each bar. The polygon points at the, let me just check this, at the right of each histogram rectangle. So if you remember, we went from the bottom left to the top right of each of our rectangles, and that's what we're going to be doing for all of these as well. Okay, and we're going to commence at half a score value below and above the respective insides of the lowest score and the high score. Okay, cool. So like we did before, we've got 0, 1, 2, 3, 4. And on my relative frequency column, or my cumulative relative frequency, we're now just going to go, so it's 0.1, well actually 0.1 and all the way up to 1.0 or 1. Okay, cool. So like we did, we're just going to create those columns. So here we're going to do half a column either side. So here for the first one, At 0, I go all the way up to 0.1. Then at 1, it's 0.3. 2, it's going to be 0.6. At 3, it's going to be... oh, hang on. Have I done this right? 0.3, 0.6. And at 3, it's just going to be 1.0. So here, I realize I don't have 4. My bad. 1.0. And so that's how we draw our cumulative relative frequency histogram. Okay? Just like we did with our cumulative frequency polygon, or our ogive, what we do here is we just go from bottom left to top right of these rectangles. And so my ogive is going to look something like that. Okay. Now, if you remember, our ogive is actually quite helpful for us in actually finding our median and also our quartiles. Now here, it's even easier because if you remember, so the definition that we have here, the quartiles divide into 4 equal parts. Now, what the probabilities tell me, and the cumulative probabilities tell me, is what percentage or what proportion of all the scores have happened up until that score. And so if you remember, the median is just the middle score, or 50%. That corresponds to a probability of 0.5. And so here, if I want to find the median, what we can just do is just go to where 0.5 is on our ogive and just read down at the score. So here on the cumulative relative frequency polygon, find the location. If we want to find the value of the first quartile, so this is the first quartile, and then we'll talk about the median later on. Find where the cumulative frequency is equal to 0.25, corresponding to Q1. So what I want to do, if I want to find the first quartile, is I go to where 0.25 is on my cumulative frequency, relative frequency. So here, if you have a look, 0.25 is over here. And so if I want to find the first quartile, what I can do is I can just go across to my ogive, or my cumulative frequency polygon, cumulative relative frequency polygon, and just go across and read down at the value. And so what that tells me is that this point here tells me, well, I'm in the first the column for 1, so Q1 is equal to 1. Okay, and so that's what we did here. We drew a horizontal line from the vertical axis where the cumulative relative frequency is equal to 0.25 to the polygon, and draw a vertical line, which is what we did as a final step from the polygon to the horizontal axis. And we can do the same for our median and also our upper quartile. And so here, the median is when the cumulative relative frequency is 0.5. And so we just do the same step. So here, I go to where 0.5 is, draw a horizontal line, and then read down. And so my score here is 2. And so what that tells me is that my median is equal to 2. And the final thing is our upper quartile is where 75%. So I'm going to go 0.75. So over here, and then go down. And so what this final bit tells me is that Q3 is equal to 3. Okay. So that's how we can use our cumulative relative frequency histogram and polygon, wow, that's a mouthful, to actually help me find our quartiles. And so that's actually, that's what we're going to go through in the following question, I believe. Okay. I'm actually going to leave this for our online class to have a go at. This one is actually quite a long-ish question, and so we're going to have a go at that actually, no, let's have a go at it now. Okay, so, for town planning purposes, the number of cars owned by each household in a suburb was recorded from the census data. The results are displayed in the relative frequency histogram and polygon below. So this is a population, so the relative frequencies are probabilities. So here, our relative frequencies are probabilities. So what this tells us is the probabilities that each household would have this certain number of cars. So let's have a look. It tells me that if the number of households that have 0 cars, it's a probability of roughly 0.25. So there's a chance, 0.25 chance of a household having, 0 cars. That's what this relative frequency histogram tells me. Let's answer the question. Oh, I've actually given you this. What fractions of households have no car? Well, what I just said was that here, when I look at this relative frequency, it tells me what the probability is of a particular event happening. So in this case, that is no cars is 0, 0.25. We just want to write that as a fraction, which is just 1/4. Okay. Next part. Part B. What fractions of households have fewer than 2 cars? Now, fewer than 2 cars just means I can either have 1 car or no car. So what I'm going to do is I'm going to look at the columns for 1 car and no car. Now, if you have a look, 1 car is this one here. 0 cars is here, and that's 0.25. And 1 car is this column here. And that one is roughly 0.5 if you have a look at the graph. And so if I want to find what fraction of households have fewer than 2 cars, I'm just going to add those two together. 0.25 plus 0.5, and that's going to be equal to 0.75, or as a fraction, 3 over 4. Okay. The next part. What is the probability that a household chosen at random has 3 cars? And so once again here, we're just going to go to our third column over here, and we're just going to read off what the probability is. Now here it's just halfway in between, so that's 0.125. Okay. Next part. Town planners will advise that additional on-street parking will be provided if more than 40% of the households have 3 or more cars. What we want is 40% of the households to have 3 or more cars. So 40% is just 0.4. And so what we're going to do is we're going to go to the columns with 3 or more cars, and we're just going to add up their probabilities together. So let's have a look at 3 or more cars. So that's going to be this column over here and this column over here. Now, we want to just read off their frequency. So 0.3 just happens to be 0.125 plus the 0.4 column. Now, I'm not quite sure if you can see that quite accurately, but I believe when I did this question earlier, that was roughly a quarter of that first up until here. So that is 0.025. And so this gives me a total of 0.15 or 15%. So 15% of households have 3 or more cars, which means that no additional parking. Okay. What we can do from here, we're going to just answer the rest of this first page, and then we're just going to answer this next bit, and then I'm going to do the rest in our online class. Okay. Complete the following table for the probability distribution. Okay, so here's the probability distribution. Just all we're doing is just filling it in with our relative frequency. So here 0 is just 0.25, 1 is 0.5, 2 is 0.125, 3 is what did I say earlier? 0. What did I say? 3. Oh, 0.1. And the last one is 0.025. Okay. I'm going to go through the rest of the questions in our online class because I do want to move on to the next part, which is a new concept that we're going to actually introduce here. So let's flip a couple pages to this example over here. So we're looking at page, so on my booklet it says page 10, but I think in your booklet it's a little bit different. It's page 11 on your booklet. Okay, this is on page 11. Here we're going to introduce a concept called the probability density function. And so this is where our the stuff that we looked at in integration is starting to come in. So this is for this whole topic is called continuous probability distributions. Earlier, when we looked at probability distributions, we looked at discrete probability distributions. Now what we're going to be looking at is what happens if we do continuous distributions. Now, let's just have a go at filling in the spaces. Now, as the number of values in the discrete distribution increases, the graph of the distribution starts to resemble a curve. And so with our discrete probability distribution, we had each of our outcomes, and we listed out different outcomes for an event. And we noticed that they had different probabilities. Now, the more accurate your scores become, so if we start to get more accurate scores, so for example, let's say we instead of having 1, 2, 3, 4, we decide to go up by 0.1, 1.1, 1.2, 1.3, and so on. The more measurements that you get, the more data points that you have, and suddenly just your distribution starts to look more like a curve than it does an actual kind of separate columns. So here, notice here at the beginning we've got less scores, so less columns, and we've just got, it looks like individual columns. But the more that you get, the more it starts to look like a curve down here. So Such a curve is the probability density function. So we call this particular curve the probability density function, and the notation that we use here is f big X of x, or in your textbook it also calls it p of x. In mathematics, in the Maths in Focus textbook, it calls it p of x. And this describes the probability distribution for a continuous set of data. So the thing here is, earlier we looked at discrete data. We looked at discrete things. So for example, when we, in the example that we looked at for the traffic lights, you could only get discrete values. You could only get 0, 1, 2, 3. You can't get 1.5 times, you can't, I forgot what the name of the lady was, but in that example, you can't reach the traffic light, you can't hit 1.5 times red traffic lights. But with continuous data, you can have all of those numbers. You can have every single number over a range. And so here, when we are looking at a continuous set of data, the probability density function is the thing that describes the probability of our particular variable. And so here, the analogy in the discrete case is P of big X is equal to X. And the important note is often, instead of writing f of big X of X, we just abbreviate to f of X. Okay. So over the page, we're going to talk about a few properties of this probability density function. Now, for continuous random variable x on the domain a to b, so what this means is when we have a random variable on this domain, so a and b are just the limits of outcomes, so allowable outcomes. So there's the range of my outcomes I have for my particular event. So what we want to do here is, if I want to find the probability of an event happening, instead of doing, earlier we said P of X is equal to X, so that's a probability of a random variable being equal to X for a discrete value. What we want to do here is the probability of an event being between two particular values. So the one I like to think of is height is a good example of continuous data. So height is this, like, we could use height to represent this particular we could use this continuous our probability density function to tell me about describe a height. So what this is actually asking me to find is, if I want to find the probability of someone being between two different heights. So if I want to find the probability of a random variable being between two given values, the way that we do this is we find the area under the curve, and this is where our integration skills come in. Now, if we're trying to find the probability of an event, we actually need to integrate the probability density function. So here, this is the probability of an event being between C and D. And the way that we do this is we find the area under the curve. So the area under the curve actually gives me the probability of that event. Okay. And now the probability, the properties that we have about this. The first thing is our probability density function always has to be greater than or equal to 0 for all the values in our allowable range. And the reason for this is because, well, probabilities are never 0. And so here we're actually going to say, well, because this probability is actually cumulative, so cumulative, I'm going to write here cumulative probability never decreases. Okay, that's the first property that we have. So our probability density function is always going to be bigger than 0 on our domain. The second thing is, if I take the integral from a to b, so my whole domain that my probability density function is on, that will always equal to 1. And the reason for that is, well, because that's the total probabilities of all outcomes. So if you add up all the probabilities of all the events in a particular for a particular event, it's always going to give you a probability of 1. It's always going to give you a total of 1. The other thing is P of big of X is equal to X is always going to equal to 0. I'm not quite sure about this one. I'll check that up for you and then and hopefully give you an answer before our online class. And the final thing that we're going to need to know is the mode of distribution. So the most common score of our distribution is the x value where the local maximum occurs. So if we want to find the most common outcome, what we want to do is we go to the highest point or our local maximum of our probability density function. So here, this value here, or this x value here, whatever this value is, let's call it e, that is our mode. So what we're going to do is we're going to go through a few questions actually going through this. So let's have a look at a couple of examples over the page. So first one, consider the probability density function f of x is equal to x squared over 9 for x being between these values here. Part A, draw a sketch of f of x within the defined domain. So what we want to do is I just want to draw a graph of this particular function on the domain 0 to 3. So I'm going to draw from 0 to 3. So I'm going to go 0, 1, 2, actually let me spread this out a bit. 1, 2, 3. I just want to draw this graph. Now, if you have a look at this function, I've got x squared over 9. This graph is going to give me a parabola, and the center of this parabola is going to be at 0. Now, the other thing that I might want to check is just check what the final, what the y value would be at 3. So what I'm going to do here is, so here we have the f of x probability. Ooh, let me just check something. So this is my y. Y is x. I'm just going to sketch this out. This should look like a parabola, and so it starts at 0, and at x is equal to 3, we have a y value of 1. So this is 1. So there we go. Yeah, it should look like this. So that is what our probability density function looks like when we sketch it out. So this is just a parabola, and I just, for this value over here, I just subbed in x is equal to 3, and we got 1. And so we drew this parabola here. Part B. Check that f of x is a valid probability density function. Okay, two conditions here is f of x is greater than 0 for all of my values on my domain. If you have a look, it's above the x-axis, so f of x is greater than or equal to 0 for all x, for 0, x, 3. So that's my first condition. That ticks off. The other thing is when I integrate this between the two limits of my domain, that needs to be equal to 1. So what I want to check here is I want to check whether or not this is true. The integral of this function between 0 to 3 is equal to 1. So let's actually do this. So this just becomes the integral of 0 to 3 of x squared over 9 dx. And when I integrate, I add 1 to the power and divide by the new power. So here, when I add 1 to the power, I get x to the power 3 over, I would divide by 3. But because I've also got this 9 at the bottom, I can just divide by 27 here. Final step, I just need to substitute these values in. So I get 3 to the power 3 over 27 minus 0. And that's 27 over 27, which gives me 1. Exactly right. That's what I wanted to find there. So that's how we check if our function is a valid probability density function. If we want to check if something is a valid probability density function, we want to check that f of x is greater than or equal to 0 on our domain. And the other thing is we want to just check that the integral on our domain is equal to 1. So those are two things we want to check here. The final part is I want to find the probability of our random variable being between 1 and 2. So what I'm going to do here is I'm actually going to just, if I want to find the probability of our random variable being between those two values, I'm going to just integrate with those limits. So what I want to do is I actually want to find the area between 1 to 2. And so here, for this part, what I'm going to do is I'm just going to go, okay, probability of our random variable between 1 and 2 is just going to be the integral of 1 to 2 of our function x squared over 9 dx. Okay, so what I need to do here is I just integrate it x over 3 to the x to the power 3 over 27, and I'm going to substitute my two values, 2 and 1, substitute them in, 2 to the power 3 over 27 minus 1 to the power 3 over 27. So this becomes 8 over 27 minus 1 over 27, which becomes 7 over 27. So that's how we find probabilities using our probability density function. We actually need to integrate and set up a definite integral with those two limits, depending on what the question asks me to do. Okay, let's have a look at the next question. The diagram shows the graph of a continuous probability density function below. What which of the following is the mode? Now the mode is the most common score. And so what we said was that the mode, if you have a look at the notes above, the mode is the x value where the local maximum occurs. So what we're looking for on our continuous probability density function is the local maximum, the highest point on our continuous probability distribution function. So here, if you have a look, local maximum is this point over here at 0.8, 0.6. And so what we want to do is we want to actually find the x value of this particular point. So if you have a look, x value is just 0.8, 0.8, and so my answer here is just going to be C 0.8. Okay, so that's how we answer a few of these questions on our continuous probability density distribution, continuous probability density function. If we're in particular, what we want to do is we want to be able to, when we are trying to answer these questions, in particular, if we're trying to check if it's a valid probability density function, we want to check that it's greater than 0. Our function is greater than 0, and we want to integrate between our two boundaries and just check that it's equal to 1. If we want to find the probability, we just create a definite integral with those limits. And if we want to find the mode, we just want to find the x value of the local maximum. So hopefully that helps, and there should be a few questions for you to have a look at. In our online class, we're going to go through a few more questions on this, just to get us a bit more acquainted with the continuous probability density function. But if there's any questions, feel free to send me an email or send a link, put a comment below. And until next lesson, Year 12s, as always, stay safe, stay healthy, and stay wonderful, and I'll see you in the next video. Bye!